welcome back and happy Friday. It is an amazing day, isn't it? Actually, last class, we finished something amazing regarding estimating the state of something. It's called Kalman filter. With Kalman filter, we finished that chapter. Which chapter? Chapter of dependencies between two random vectors, chapter of linear transportation of random vectors. We also even finished the conditional mean and conditional covariance. Conditional mean and conditional covariance are two complex things that always we have, because when we have conditional means something given something, some dependencies coming in this between. And it's two random vectors and has lots of applications. Why? Because a state is, for example, one random vector and measurements another random vectors, and you are dealing with relationship between measurements and state and those things, and we modeled that very beautifully using Kalman filter, and that was amazing. And I hope you can use those in other application as well. But you also have next assignment. You need to use that. When is the due date? Tuesday? Yeah. Okay, so you have time, but please start it as soon as possible. If you have any questions, just let me know. Yeah, that was something that I want you to take out from this class, at least till now. But from now, we're going to move one dimension higher. When I'm saying one dimension higher, really one dimension higher. You know, we talk about random variables already, that we said, okay, we have a variable like x is a random. So if it's random, means it has some distribution and some mean. That my examples are in Gaussian, but because Gaussian is nice and you know, the shape is very beautiful and smooth and nice. And then we said, okay, what about have random vector? Instead of x, we have x and y, x dot, velocity, x dot and y dot. That become a vector, and then this one dimension curve become ellipsoid. And this ellipsoid, you can get lots of information from the ellipsoid. And right now, we want to move one dimension higher. We want to add the time dimension. We didn't talk about time before. Maybe a little bit. Like when I said, what was that? Bernoulli distribution. We said, okay, we are repeating some, you know, random things, like multiple time dropping, you know, coin. Anyway, that was kind of dealing with time, but here we really want to talk about time. So we're gonna have time. So this random vector eventually gonna get a function if we move in time. When we increase time, in this time k is here, this robot, this is the position of the robot. The example that I'm saying, a real example, x dot, y dot means position and velocity of the robot that is moving. So it can be in t k plus 1 here. ek plus 1. And moving this direction, so the ellipsoid is like that, and this is making a function. And we are moving from one variable to multiple variable in random vector. We are using to the function of these random vectors, a function of random vectors. And we want to see how these random vectors changing in time, like that. Here is Gaussian. So as you can see, it's very smooth, but it's not always smooth. It depends on the distribution. So in this case, you had that bell shape covariance type. In vector, you have an ellipsoid shape. But what is the shape in the function? Maybe in the function, we also have something. Let's see. Yes, we have. I think some of you guys use this for one of your assignment, and I was surprised. Oh my God, these guys are so moving fast. So this is, like for example, this is the covariance. It's showing how this function can vary around this bound. That green bound that I mentioned, this function can go in this and make thousands function. So that's a variance or covariance. Covariance of random process. And this is random process. I just wanted to let you know we are starting a new chapter. And lots of applications in signal processing. This can be a signal. This can be a position and trajectory of a robot. And even can be a function of optimization. This is you can optimize this function. I will tell you how eventually. How we can optimize this function that, for example, makes best way to go from somewhere to somewhere. That, for example, if the soil is not good, we find the area that the soil is better, that robot can pass easier. Or if the area in the ocean is wavy and, for example, current is there, we not go there, we go another place. Not get involved with losing energy. That's an energy consumption factor. So those things all can come inside this path, this function. You have multiple choice in this function. You choose the one with minimum cost. Okay, so that was the ultimate of this class. What we're going to get from these random processes. I just want to check if I am recording, because last class I recorded that, but wasn't there. I don't know why. Just going to discard this for a second. Back to the class. Yes, this is what we want to talk. Random processes. We're going to deal with the functions that evolve over time. But most of topics starting with random processes start with very simple process that is a Bernoulli distribution. We talked about Bernoulli before, and we said, oh, that's a very simple distribution because it just have two outcomes, 0 and 1, like and probability of being 1 is p, and probability of not being 1 or be 0 is 1 minus p. So this happen a lot in so many applications in our electrical and engineering applications, because, for example, you are sending a signal as a sensor to detect object, you get result or not. You are sending data in a network, it receives in a destination or not, and multiple time doing that. And sometimes you need to see how many times I send it to get result, or talking about the time and numbers. Oh, the number, that's the important part. In Bernoulli, you are talking about numbers. And numbers are something that we are dealing with soon. Okay, so that was Bernoulli. We had it before. So Bernoulli distribution is a discrete type of distribution. So it means it has, it doesn't have a continuous function. It has a mass function. So you just have 0 or 1. Like here, we did multiple trial n times, and every time we did trial, and we got 0, 0, 1, 0, 0, 0, 1, 1, 1, and this is the, and we did it many times. So why the Bernoulli is a process? Why is not just random variable? Because time is involved, isn't it? When we do trial in time. Like we are doing that in time, multiple time. For example, where you have a coin and you toss a coin multiple time, it means do one time now, one time another time, one time another time. It can be one after each other, or there is some time involved anyway. So that's why it's a process. So if you have time involved, the random variable becomes random process. And this is random process, but the simplest one. Why is simplest one? Because the outcomes are just 2. And we just have one variable is p that is showing probability of success. And what is probability of not success or failure? 1 minus p. Easy. Because of complement rule, to remember. So that's Bernoulli. But Bernoulli is the base. So many applications, like coin, tossing coin is one of applications. You always use it. Packet arrival is another application in communication. Sensor triggering, on, off, that's another application. But the main application is that Bernoulli is just a stepping stone for most of amazing applicable distributions. You're gonna see that. Yeah, it's building block. Building block is better word. Building block of discrete time random events. However, we need to move from discrete to random. Yes.
Just one of the people online says they can't hear you, so you know.
Really? They can't hear me? Okay. Numbers is, actually I can say this is the only distribution dealing with numbers. However, we're gonna move that to the continuous form that called Poisson, sorry. Forgot the name of Poisson. Sorry, Poisson. Yes, we're gonna move to Poisson. Eventually, Poisson is a continuous version of this. And the continuous version of this is gonna be Poisson, and Poisson is amazing. And it's dealing with numbers. Anytime number is involved, Poisson coming. Like for example, in radar, it happens a lot. False alarm, of course. When you want to see, for example, we want to model false alarm, outliers. because number involved. We want to say, okay, in this, for example, radar environment, the possibility of having false alarm, the number of false alarm is limited. It can be infinity. It's just numbers limited. In that case, you can model it using Poisson. That Poisson is a continuous version of this that we're going to talk today. Anyway, that's the numbers. We had that before, binomial. We can play more with that. We can play more with Bernoulli. If we play a little bit more, we can get geometric random variable. Geometric random variable is if when you want to see, for example, how many trials to get the first success. First success. You want to see, for example, how many try, M is how many try to get the first success coming from that. They are all variation of Bernoulli. So that's why Bernoulli is important. So if I want to explain a little bit these diagrams, we had them before. So the number of success is actually, for example, you want to see probability of k time, because number of success, probability of, so first success is this much, probability of k is, for example, 2 is that, and as you can see, they are actually around the mean, and that mean is coming from the p. In that example, p was 0.3, so that's why there is a little scoot to this side. It's not exactly in the middle, it's a scoot because of that 0.3. So we had that before, and for geometric is also something similar. If you want to explain this, I explained it in the lecture note, I think. So that's for geometry. We had that before. I just explained this again because it's very similar to things that we want to talk today. That is Poisson distribution. Okay, so let's move from Bernoulli to Poisson. So the Poisson is a continuous version of Bernoulli. Bernoulli is discrete distribution, 2 outcome, and 1 p, probability of success, and 1 minus p, probability of not success. Imagine, because we do trial and the time coming, imagine these trials happen after delta t time. You know, every delta t time we do 1 trial. And the success probability is p. So the rate of success is probability of success divided by t. So that's called rate of success. Imagine when we want to make this continuous, we need to make the delta t smaller and smaller. This is how we move from continuous to discrete to continuous. If the trial is happening every, for example, second, we make it millisecond and nanosecond to make it more continuous. So here, do the same. We make delta t smaller and smaller to get, so delta t moving to 0. But because this success rate, this rate of success need to stay constant, we also move p to 0 at the same time. So we limit p and delta t to 0 to stay this lambda constant. That lambda is a rate of success. That's lambda, not x. That's lambda. So this makes the new distribution. So the new distribution called Poisson process. So from Bernoulli to Poisson, you just need to make delta t smaller and smaller. And to make this actually lambda, this is lambda, yeah. This lambda constant, so you need at the same time move p to the 0 as well. So let's see what's going to happen. Okay, if delta t going to 0 and p going to 0 as well, so the rate gonna stay constant. So that's what I explained. Then the number of events in t interval or the time t follow the Poisson distribution. So this is the Poisson distribution. So what it's saying is saying the number of events that I can write here, number, remember, number is the main part. Number of events in a time t. So we have two variables, t and m, and this rate is constant. Rate is constant. So what is telling us? This is called Poisson distribution or Poisson process. It's a process because time involved. When it's time involved, it's Poisson. We want to see number of success or number of events that make success events in a portion of t. So it happens a lot. Like for radar, as I said, you want to see how many times you can detect the target in 1 second. How many times you send signals and that signal is receiving by the receiver in the t time, for example. So the rate of success is given, the rate is given, that is constant, most of the time considered constant. However, we're going to talk about that type of Poisson distribution too, homogeneous Poisson. Anyway, this is Poisson distribution. So how we can get this formula is not very complicated. If you go back to its grandpa, and grandpa is a Bernoulli, and write this up and do limit, if the p and delta t going to 0, you can get this formula after some series. You need to play with the series of numbers because series of numbers always add up to exponential family. So you're going to get that. We're not going to go in that, but if you want, I think it's in your, I'm not sure if I put it in your lecture note, how to prove this. But who cares about the proof? You just need to use it properly. That's the point of this class. So the Poisson process is a continuous time limit of Bernoulli process. So normally what is saying, number of events in time t, number of, for example, sending signals and receiving signals properly, all of those used in actually Poisson. So Poisson distribution is, we work with that a lot. Like one of the applications here I mentioned in sensor detection. So suppose we have a radar sensor that continuously detects objects. So we are saying continuously, but the radar is not continuously. It has some delta t that's sending and receiving to detect the objects. So, but if this delta t is very small, like for example, the delta t here is 0.001 second, like 1 millisecond. Like each scan is in 1 millisecond. We consider that as still Poisson. That's okay. It's still close to 0. And we also have the rate, we also have the detection, probability of detection, that is P, 0.02. And the rate of detection is 2. So it means in each second, 2 detection per second. We can have 2 detection per second. So this is the rate of detection. We know this information. This information coming from the sensor. What we want to find number of detection in 10 seconds, or distribution of number of detection in 10 seconds. So if the number of detection be m, so this m follow the Poisson distribution. So t is given, we put t, we have lambda, we have t is 10, so the lambda is 2, t is 10, we put that in a formula, and this is the distribution of actually m time detection in this 10 seconds with the probability of rate of detection 2. This bell shape, because of this exponential, is very similar to the Gaussian distribution. You can see that here in this shape is belong to that. So as you can see, the time, for example, this is a number of events in between 0 to t, and t can be like 10 here, and you also can find mean and variance. So the mean and variance in Poisson distribution are very similar, exactly similar actually. Sigma t, sorry, this is lambda t. This is lambda, yeah. Lambda t. So we have lambda and t, so 20. As you can see here is exactly the mean is 20. We can explain that later how we can compute this, but they are all easy to compute. Okay, so I don't start homogeneous Poisson. Let's talk about homogeneous next class. So, but this was the start of actually random process. We're gonna see the application, especially Gaussian process. If we talk about Gaussian process, you can see lots of application coming up from Gaussian process in AI, in machine learning, you can use Gaussian process. And for robotics, you can use Gaussian process. I use Gaussian process a lot in my research and papers. And yeah, I had more than like 5-6 papers, maybe more, just related to Gaussian process. Because you can model everything. Even I modeled the street lanes with Gaussian process, like for self-driving car. Or multiple Gaussian process make, you can have multiple Gaussian process that are depend on each other. Like lanes are like that because they are parallel. We have that as well. For robotics, you can model the path using Gaussian process. Why is Gaussian? Because this position to the other one follow the Gaussian rules. And for image processing, for robotics, so many applications. AI, you can use that. Okay, so we're gonna talk about that next week. Any questions? Yes.
The Poisson process.
Yes.
Is the expected value of m and the variance of m always lambda t?
Yes. Yes, it's always that. But we're gonna the next class we're gonna kind of prove that.
Okay.
Why? Yes. Expected value and covariance, variance actually both same. Both of them, as you can see here, E of m means mean. Actually, Poisson distribution and variance and E are same, as you can see. It's very interesting. this Poisson distribution is very interesting. It has lots of things more. We're going to talk about that next class, coming with homogeneous Poisson.